Here's now a little discuss after those applications. Let's discuss sensor clouds in a little more detail. So here's the idea of a sensor cloud. You have all your sensors. They're publishing their data to the cloud. And so because they are actually erratically publishing data, each of those data is by definition an event, then it's natural to use event processing software, and then we so-called publish subscribe software. So the basic idea of the architectures we have for this type of problem is a network of distributed publish subscribe brokers, which then gather where sensors publish the data to the brokers, and then the filters, the transforms, the transformation agents are going to take the data from sensors and turn it into information and knowledge. They subscribe to the sensor data they want, and then they produce refined data, which is then notified back to either desktop clients or to particular applications and so on. And this, I should point out, this is naturally collaborative, because once you've centralized all these sensors in the cloud, we can actually be notified all sorts of different applications, so you can get natural sharing of this data. This underlies effectively the architectures of activities like WebEx or Adobe Connect, where say the host is presenting on their PowerPoint, that PowerPoint is transmitted up to the cloud, and then it's notified back to all the people sharing that information. There's been a change, and that change then appears on your desktop. Here's that architecture in a little more detail. We originally used some software we wrote ourselves called Narada Broking to do the publish subscribe. Now we use well-known open source software like ActiveMQ or Netty to support this idea. When we did Narada Broking, these were in early days, and we used the fact that we wrote our own software to support particular protocols, such as those needed to do audio-video conferencing and provide the optimized support. So as well as the distributed broker, we're doing the control. We also have the data effectively being done separately, and this is an important idea when you do these web services. You make certain that you send the data to something which has the bandwidth to process it. And you can usefully separate control and data services. You also need to be able to do a lot of management. You need to know how many sensors you have, what their properties are, and provide a nice interface so people can probe the system and see which sensors they want. Here's some old examples we did with a company, Anabas, where we have multiple Lego robots with various sensors on those robots, and then including the RFID and the GPS. Those will all sent back to the cloud and plotted out as you can see here, and then use the GPS to locate this the position of these sensors. These particular things are from Hong Kong, which is what you see the location as here. When you look at the performance of these brokers, here we were looking at high-end sensors, roughly equivalent in bandwidth to an MPEG-4 webcam, or the Connect, which is around 1.8 megabits per second for each instance. That's pretty high bandwidth. Then here was as you looked at the number of clients, we had the sensors hosted on OpenStack using virtual machines. And you can see that basically the latency is relatively small, till around 150 clients when it gets a little out of hand. So you can, if these very high bandwidth clients, you can put 100 on a broker. That doesn't mean you can only have 100 sensors. It just means a single broker can only handle 100 sensors. All of these publish subscribe systems allow you to use multiple brokers, and they establish the appropriate management to allow the brokers to coordinate with each other. Here's some discussion of radar data. This comes from our work with Kansas, where Kansas either typically flies on aircraft radar. Those radar observes the Earth, or which actually observes the North and South Pole. the ice, they observe the ice, and then they probe the ice and see the ice bed, and this allows them to provide the boundary conditions needed in models of the glaciers to study glacier and ice sheet dynamics. There's a picture here of an internet connection. Actually, the North Pole and South Pole do not have good internet connection, and so these are a pseudo Internet of Things, because typically the internet connection is done by taking the data from these sensors, putting them on disks, putting the disk on a plane, and running the plane back to the continental US, and then we can put it all on the internet. Here's some pictures of this is done by the UITS at IU. They built all this stuff. Here's the internet connection. Here is the cyber infrastructure used to process the data from these radar. And this is all packaged up before it's shipped to Greenland to do some measurements. These are all laptops and servers and disks and things like that. You get through a lot of disks in one of these field expeditions, because a disk is relatively tough exposure for the disk in this world. When we take all this data, we then do analytics on it. This work is done by Jerome Mitchell and David Crandall. There's more details of this in the radar informatics section of this course. You do things like is illustrated here. We take analytics method. Here's one based on some earlier work, which basically takes these pictures, which are the radar pictures from these sensors, and tries to find the layers. In this case here, this is the ice air boundary, and this green, that's the red, and the green is the ice rock boundary with the bottom of the glacier. It's pretty rocky at the bottom of the glacier. And these are versions done by human beings, and here versions done by computers. And so here the data analytics is finding layers in images. So you get huge numbers of images, and you want to do image processing on them. At some crude level, that's what the pathology problem is. There you get lots of images representing where you try to scan for tumors, and that's again an image processing algorithm. It's important to note that when we have these sensors, we need to put them in the field. There are lots of issues like the amount of power being limited. And so it's interesting to look at the use of GPUs, which are more power efficient. And here's some plots of the speed up you get on a GPU. So rather than having several ordinary Intel CPUs, you do add a GPU and get more power, or I should say, get as much processing as you wanted, but at lower electrical power cost. So there's the types of things one wants to do in this area. Here's an example of another use of sensors here in observing the ocean, where you have lots of sensors and robots running around the seafloor, gathering, sending the data up, and the so-called Ocean Observatory Initiative has a cloud-based architecture for storing all this stuff, and then you analyze it on the Azure cloud and then send it back down to your computer. So this is just typical of many related applications of this type, because you don't just have sensors in the oceans, you have sensors in the forest, you have sensors in your cars, you have sensors in your homes, you have sensors in you, and all of those are going to go up into the cloud and get analyzed. Here is another related one for so-called remote sensing geoscience, where again they're taking more different imagery from lots of locations, processing the image to form complete pictures, and then these are natural types of pleasingly parallel application, because each image can be done separately, and they run very well on clouds, in this case the Azure cloud.